Thanks a lot for the introduction. Yes, I'm Katya and I will be talking about contrastive feature learning for fault detection in diagnostics today. Well, regardless of the exact industrial asset that you want to maintain, we all are profiting from the increasing investment in condition monitoring devices. As this gives us a lot of data, hopefully real-time data, that holds the information of the current health condition of our asset. To name a few examples, here we see a bearing that is monitored by accelerometer sensors, and we see a few sensor responses under different health conditions. Or here below, we see an example of these railway wheel sleepers, which are monitored by a camera that is attached below a diagnosed vehicle. And we see 3 images, and you can guess which are defect or not. 2 of them are defect. Or here we see some sensor response from strain gauge sensors, which monitor these railway wheels, and these sensors are fixed installed in the railway tracks. So we gather all of that data, and this data gives us the possibility for a purely data-driven solution to fault detection and diagnostics, if we have sufficient data available to do that. And I claim this is hardly ever the case. If you look at condition monitoring data, there are actually a lot of factors that cause variations of fluctuation within it. Of course, there are the health factors. These are the ones that we are interested in. So, for example, fault type and severity will have a certain pattern in the data that we exploit or which we use in order to detect and diagnose faults. But there are also a lot of other factors that also cause variations in the data, such as different operating conditions, or also some uncontrollable factors being like, for example, ambient temperature might affect the stiffness of your asset, and that might also translate back to the sensor readings that you have available. So sometimes at a certain task, it's not that easy to distinguish these different kinds of factors. So we're interested only in seeing the variations caused by faults, for example, but actually sometimes it's not so easy to distinguish these. And it especially gets harder if we have a training data set available that is not very representative of all future conditions that my asset might endure. And I claim this is very often the case. Just to tell you a few examples. Of course, you know, within the specifications, you know at which operating conditions your asset can operate. However, it is not really realistic to assume that you have the time to record a data set which contains all possible combinations of operating conditions. If you look at the environmental factors, the ambient temperature I simply cannot control. So if I record the data for 4 months during the summer, the data might look different if it's recorded in winter. Of course, it depends on the asset also. And even if you look at what we actually want to detect or diagnose, being the faults, I think in most of our assets, I hope that's the case, that faults in operating industrial assets are actually very, very rare. So often we do not have a lot of fault data available. And even if we have fault data, and we know this and this fault occurred already in the past, we never know if not in the future another fault might occur. So we want the model actually to be very sensitive to fault patterns, but also to potential novel fluctuations that might indicate that there is a new fault. So this is objective 2. However, we don't want the model to be hypersensitive to novel fluctuations, because they might also be caused by, I call it, the other factors, those that are not related to the health condition of the asset. And these are the 2 objectives that we have set ourselves, and how can we achieve them. And we decided to try to achieve that by learning a suitable feature space. So what we did, we trained an encoder model, which is simply a convolutional neural network, where we pass the condition monitoring data that we have and just project it into a smaller dimensional space. And we want to do it such that we can achieve both of these objectives. And we do this by employing the triplet loss. As the name says, the triplet loss is calculated on top of a triplet of data, basically. I will just walk you through one example. Let's assume I want to calculate the loss for one sample that I call the anchor. So I pass it through my encoder and I see where it's positioned in the feature space. And then within my batch, I also select a positive sample. Positive meaning, in our context, having the same health condition, but maybe, we don't know, maybe being recorded under very different circumstances, under very different operating conditions, and so on. So we also pass the positive sample through our encoder. And now, in order to achieve this invariance to these other factors that might vary between the anchor and the positive, we force, in the loss function, we force these two data points in the feature space to be very close together. So this is the first term of the loss function. And then in order to make the triplet complete, we also select a negative sample, which is basically defined as having a different health condition as the other two that we have. And in order to achieve the sensitivity of the encoder model to fluctuations in the data that actually correspond to a health condition, we want to position that very far away from what we have seen before. Of course, we regularize it also, so it's not, we don't push it too far away, but this is basically how we want to achieve both of these objectives. So this is the loss function that we use to train our encoder model. And once we have trained our encoder model, we will, dependent on the task, I will explain you the applications we applied it to in a second, but we will either classify or classify and cluster the feature space. Speaking of the applications, it's clear, I think intuitively it's clear for everyone that the better the data represents all of the potential future factors, the easier the task is of achieving both of our objectives. But as the training data representation or representativeness basically decreases, it gets harder and harder to do it. Right? If you have no fault data available at all, how can you make a model that is very sensitive only to fluctuation coming from a health condition? So within this scheme, we looked at different application cases which have, with respect to our objectives, increasing difficulty. So in the first one, we will assume that we already know all fault data, that we have data of all future fault types that we want to classify, basically, and also from the other factors we have a sufficient data set available. And then in the second one, we will have a look at what happens if we don't have that kind of data available, where we have only a subset of possible operating conditions and a subset of possible fault data available at training time. And last, the hardest one would then be, what do you do if you have absolutely no fault data available to train your model? But let's have a look at the very first one. Let's start easy. So this is the classification. Since we have all faults available at training time, it boils down to only a classification task. So this is what we do. First, we train the feature space, as I explained earlier, and later on, we classify this feature space. It's simply some fully connected layers. And let's have a look at a few images. You have seen them earlier, where you want maybe guessed which one is healthy and which is not. So on the right, we see a healthy image. However, there are some rocks on the sleepers which might very easily be mistaken as a defect. As a second image, we see a crack here. I don't know if you could spot it without circling it. And in the last image, we see a spalling defect. And I think from looking at it, even visually, it becomes quite clear why these factors of variation and true defects might be mistaken quite easily. I will say this dataset we are provided by SBB, and the work I'm presenting here is now done by a master's student that is supervised, Kayan Ratna, that is supervised by me, and Lucian Anku from SBB. But yeah, the difficulty lays in the fact that actually the healthy image might be easily be mistaken as a defect, and this is why a normal classification model did not perform very well on that task. So the first result here is of a normal classification model. But if we then apply what we have introduced earlier, where we learn a feature space and later on classify it, we could gain a accuracy gain in 13%. So that's really nice. So we have covered the first case study. Let's go on to and raise the difficulty a little bit. Now we will consider we have a data set where we assume that we have only limited data available. So first we assume you have only data available from a subset of operating conditions and later from a subset of faults. And since I know I have only a subset of faults, I want the model to be able to classify those that I know, but also to be very sensitive to novel ones, to detect the novel faults. And we see if we can what we can achieve with contrastive learning. So since we also want to detect novel faults, we don't only classify the feature space, because a classification model will never be able to classify something it has never seen before, but we also cluster it with a density-based clustering algorithm called optics. Yes, and that's the data set that we applied it to. It's a varying data set that is recorded under 4 different loads, and it has healthy data as well as 3 different fault types, each at 3 different severities. So it gives us the perfect playground to test our objectives. So first, we take out all data recorded under a specific operating condition. We train the model on the remaining data and then test how does it perform on the one that we have taken out. And second, for the second objective, we train a model on a subset of the fault type. So we take out actually all data corresponding to a specific fault type, train the model again on the remaining data and see how does it perform if how does it react now to this novel fault type. So these are the 2 experiments I will show you now. In the first, we try to achieve objective 1, where the model is invariant to other factors, and the other one where the model is able to classify but also detect novel faults. Again, I will explain it I can say it here again. Looking at case study 1, objective being invariant to other factors. So how do we test it? We train a model on a subset of operating conditions. So we took all data from one operating condition out, trained the models, and then evaluated it on the known operating conditions, the same that the training data set has been recorded, but of course it's a test data set, it's not the same data, but then also of the normal operating condition. And first we have a visual look at how do the feature spaces look. On the right, we see the feature space that is learned with a triplet loss, and on the left, we see the feature space that is trained by training a normal classification deep model. So the model is exactly the same, the backbone structure is the same, but we optimize it with a cross entropy loss. Just for your explanation, the heavier colors, basically the stronger colors, are those data points that are recorded under the known operating conditions, and the softer ones are those that are recorded under the novel operating conditions. And you can see actually both feature spaces look certainly fine for classification of all fault types, regardless if the operating condition is novel or not. However, if we now want to cluster it, because we want the model also to be able to detect novel faults if we have some, this seems to be way easier, like visually, in the triplet encoder feature space, because the class clusters are just more compact, basically. They are more cohesive, more separable. And this also translates, into the numbers. So we always show the results on the known operating condition as well as the novel ones. And for the clustering, we cluster it on all data and then report the result on the known operating condition and the known and the novel ones. We can see that the triplet encoder performs quite well in both tasks, actually. But now let's go to the second objective that we also want to achieve. to remind you, we also want to be the model to be able to detect faults that I might not have seen before, or at least tell me, well, there's something happening that I have not seen before. So we trained a model on a subset of faults. So actually we took out the ball faults of the bearing and trained the whole model on it. And then we evaluated the model on the known faults, but also on the novel one. What happens in the feature representation? And I show you both feature spaces. And like, obviously, yes, I should say the gray one and the purple one and the beige ones or the orange ones are the novel fault type under 3 severities. And what we can clearly see is that unfortunately in the feature space, the novel fault types are not separately clustered. So we cannot find a full cluster of all novel fault types, but that would also maybe be very ambitious. But what we could see is that in the triplet encoder feature space, still the original class clusters are still very compact. And this, combined with the density-based clustering algorithms, allowed us to still recover the old class clusters and detect a lot of the novel faults as outliers. And actually, 94% of the detected outliers were actually novel faults. However, many novel faults were also be classified as other fault types. So, but anyhow, from an operation perspective, if you have an alarm which tells you, well, there's something novel in the data, you should check it out. In 94% of the case, it actually did correspond to a novel fault type. Okay, this then again translates to data. Of course, the classification performance on the known faults is very good because that is what the model was trained to do. A classification model, as I said, can never classify something it has not seen before, so here the performance is really bad. But if you look at the clustering, we can clearly see that in the triplet encoder feature space, we were still able to recover the original class clusters, and the outliers are not detected as a cluster, so this value is rather lower, but we could recover the original ones, and we could detect approximately half of the novel faults as outliers, and 94% of the outliers were actually novel faults. Well, summarizing, we have proposed to use contrastive learning for fault detection and diagnostics, and we have evaluated it in different scenarios. And just to give an outlook, so this is what current work, where also I work on with a master student, Marco Ketzel. We work on the scenario where we have absolutely no fault data available for training, and we also try to see if we can apply contrastive loss on that, and the case study we're using is basically this railway wheel condition monitoring case that I have mentioned earlier. Thank you very much for your attention, and I'm happy to discuss later.